Hi there. Welcome to lecture 19 of Machine Learning from Data. We are going to take a peek at unsupervised learning. And I want to emphasize it's just a peek. It's not in any way a fair treatment of this huge area. Okay. Now let's have a quick review of what we did last time. We talked about radial basis function. So that's another important, powerful, useful model. Okay. We talked about the non-parametric RBF for radial basis function, which basically extends the nearest neighbor by looking at all data points, weighting appropriately, and then summing up the contributions from each data point. So a weighted average of contributions from each data point. Further data points from the test point have less impact on the classification or prediction at the test point. Okay. Now, that's the non-parametric RBF. There's no training. It has pretty much all the benefits of the nearest neighbor algorithm and also the main computational drawbacks. Okay. So we ended up deriving the K RBF-network. So what were the steps? The first step was to view the radial basis function as placing bumps on each data point, and those bumps were now of a fixed height. Those are the parameters, the bump heights, and then each bump on each data point makes a contribution according to the height of that bump to the test point. Okay, and when we were done with all the math, we find that the hypothesis is a linear model, okay, with tunable features, where the tunable features come from being able to tune where we place the K bumps, the centers. Okay. And we talked about a simple method for picking those centers, which is this Lloyd's algorithm, pick the centers far apart from each other so they represent the data. And then we indeed do have a linear model with the centers picked according to the clusters in the data. So in principle, it's a nonlinear model in the centers, but we don't use the Y values in deciding where to put the centers, and so we're not really fitting the centers so much, more like just organizing the centers to represent the data. Okay. And I showed you what happens if we picked 4 centers and if we picked 10 centers, and you get the usual overfitting that's possible, and so you have to regularize, and that's what we see here on the right. Okay. Now, we've already seen unsupervised learning in 2 contexts. The first was to organize the data so that the branch and bound algorithm in nearest neighbor search for finding the nearest neighbor can be more efficient. Okay, so you store the data in clusters, and then when you go into a cluster and you come out with the closest in the cluster, you might be able to bound in such a way that you don't need to search the other clusters, and that requires tight clusters that are well separated. And then we just saw the use of sort of an unsupervised technique to find the centers, as far away data points to represent the data in the RBF network. Okay, so unsupervised learning is a useful preprocessor for organizing the data in supervised learning for specific techniques that we have already developed. And unsupervised learning is important on its own because, for example, you're trying to learn a language. So it helps to just listen to the language and build the patterns. Or it's helpful for Amazon to organize books into categories, even if you don't know exactly what each category means. Okay, and last time I showed you a peek at the kinds of information that you can extract just from unsupervised clustering. So on the left, we saw the multi-class version of the K nearest neighbor algorithm that classified the space, intensity symmetry into regions corresponding to each digit. And on the right, you just cluster the data. So you don't even have access to which data points are which digits. You just know intensity and symmetry for each data point. And now you do a 10 clustering, and look, the structure is very similar to the structure that you see with the supervised version, but in the supervised version, we know which digit is which. So all that remains after we've clustered the data is for someone to tell us which cluster belongs to which digit. And so you can see how clustering can help significantly with organizing the data before you get to the supervised learning task, so that you only need a few data points from each cluster to now have a fully, functional classifier, which would be a supervised classifier that, organizes the data based on lots of data, but then a few data points tell you what clusters belong to what classification. Okay, so we're going to start with clustering, and we're going to talk about it in a little more precise framework and develop some algorithm. It's a hard problem. It's an example of NP-hard problem. In machine learning, there are lots of NP-hard problems, but still we can build efficient heuristics for clustering. And then we will talk about probability density estimation, which is another very important task. It's an unsupervised task. Okay, and you can think of it as a generalization of clustering. So let's go to the board. I left the slide up so that you can have some context for the problem we're about to define, which is clustering. Okay, so clustering. Okay, and this is an example of unsupervised learning. Okay, And so in the unsupervised setting, you still have your data, but you don't have y values. So your data set is equal to x1, x2, up to xn. Okay. Now, you might have y values, but you can always choose to ignore them and do unsupervised clustering, just like we did for the RBF. We ignore the y values to get centers. Okay. So let's first define what it means to cluster the data. So you output a clustering of the data, a clustering of the data. Okay, and the first thing when you're outputting a clustering of the data is you need to know how many clusters. Now, there are some automated algorithms for deciding what's the right number of clusters, okay, but in general, that's an open research question. So for us, for our purposes, we're going to assume that the number of clusters is given. Let's call it K, and so we call this a K clustering of the data. Okay? And it's just the output of a clustering. So what's the task? The task is to just produce K subsets of the data. Okay. Produce K subsets of the data. Let's call them S1, S2, up to Sk. Okay, so you've produced K subsets of the data. And now I want to tell you what those subsets should satisfy. Okay, and so we're going to simplify the problem. Okay, so first, the subsets should be non-overlapping. So the subsets should be disjoint. Okay, so it's much easier to formulate the problem when you're looking for non-overlapping clusters. Now, you can easily argue that, well, does that make a lot of sense in practice? So, for example, if we're organizing books, so there's the bio books, and there are the math books, and then there are the overlapping books, the mathematical biology or the biostatistics. So, in many real-world applications, you know, there is an argument for overlapping clusters, or you could view it as there's the bio-only books, the math-only books, and the bio-math books. That's three separate categories. Okay, so you can, in some sense, get away with non-overlapping clusters by increasing the number of clusters, but that could lead to overfitting and so on and so forth. So, okay, you know, there are complications when you allow the clusters to overlap. So we're going to simplify and say that, you know, the clusters must be non-overlapping. Okay. And the second requirement is that the clusters should be complete. So they should cover the whole data set. So complete, i.e., cover the whole data set. Now you might argue again that, well, you know, what about outliers? Maybe we don't want to include outliers in clusters because they will just, you know, distort the clusters and maybe pull them in one direction or what have you. Yes. So there are all kinds of, you know, modifications and enhancements to the problem definition to make it, you know, closer to practice, but that'll make it a harder problem. So let's at least see if we can, you know, get anywhere with this easier problem. Okay. So what this means is that your subsets Si intersection Sj should be empty if I is not equal to j. Okay, so that means that they're disjoint. And the union from I equals 1 to k of Si should equal your data set D. Okay, so this is condition 1, this is condition 2. Okay, and so that's it. Output a set of clusters. And you look at me and say, well, that's trivial. I'll just, you know, partition the data randomly into k subset. Okay, so we need to make this problem a little bit less trivial by saying what more is required of the clustering. So what else is required? What else is required? Okay, and now we can go back, for example, when we talked about branch and bound, what made good clusters? And this is what typically makes good clusters. So the data points in a cluster, the data points, so two things, you know, make the clustering good. So what else is required? I.e., what makes the clustering good? Okay, so one, you know, from the branch and bound, we saw that we like clusters to be tight. So points within a cluster should be close to each other. Okay, that makes them tight. So enclosed. So for example, you can imagine that a cluster has a center, and you know, within a small distance of that center are all the points that belong to that cluster. then that would make all those points close to the center and therefore, close to each other by the triangle inequality. So points within a cluster should be close to each other, and points in different clusters should be far away from each other. Points in different clusters should be far from each other. Okay, so the within cluster spread should be small and the between cluster spread should be large. Okay, these are perfectly valid, criteria that we would desire. Okay, now we are going to mostly focus on the first criterion, okay, which is we would like to ensure the fact that, points within a cluster are close to each other, as close as possible. And we let the different clusters, the distances between different clusters take care of itself. Because in some sense, once points within a cluster are very close, then relative to that, the between cluster distance is going to be large. Okay? So what this means is that we're going to formulate a clustering error. So a way to measure, how good the clustering is. So we define a clustering error. Okay. And then the idea is to output clusters or output a clustering, i.e. output your K subsets so that you minimize the clustering error. And the clustering error is relatively easy to define. Okay. So what we will say is that, okay, so we can think of, simultaneously defining for each cluster a center. So define for each cluster a center. Now we could call it mu of Sj for cluster J, or we'll just call it mu J, okay, to indicate that it's the center for cluster J. Okay, so then we can define the error, the spread of cluster J, Ej. So this is the spread, think of it as the spread for cluster J, is just the sum of the squared distances to the center. Okay. So it's just the sum for all data points xi that are in Sj. Okay, so it's the sum, okay, over all data points that are in the cluster of the distance to the cluster's center, xi minus mu j squared. You can think of this as, how large is cluster J. Okay, and now we can add up the sizes of each of the clusters. So we take the sum from J equals 1 to K of Ej. Okay, and that's the sum of the sizes of all the clusters. And we can define this as an error measure. It measures how bad the clustering is. Okay, so we can take this as an error measure. Okay, and we will say that a clustering is good if this error measure is as small as possible, or a clustering is optimal if this error measure is as small as possible. Okay, you can think of this error measure as the sum over all data points. Okay, little n is equal to goes from 1 to big N of the distance between x sub n and the center corresponding to x sub n squared. Okay, so where I'm loosely using the notation mu of x sub n means the center for the subset to which x sub n belongs. Okay, so x sub n belongs to some subset, and that has a corresponding center. And so how far is x sub n from that center? Okay, this is called the k-means clustering error. The k-means clustering error. Okay, it's a famous clustering error. It's basically the squared, think of it as the squared sum of squared deviations from your center. Okay, and our goal is to find subsets and corresponding centers which minimize the k-means clustering error. Okay, now you will see that the center corresponding to xn is well defined. Okay, and why? Because every data point belongs to a cluster. So the clustering is complete. It covers the whole data set. point number one. Point number two, a data point cannot belong to more than one cluster. So it has only one cluster to which it belongs, and so a well-defined center, and that's because, you know, the subsets are disjoint, so no data point belongs to more than one cluster. So these two sort of requirements are in some sense instrumental in even just defining this error function, making it well-defined. So let me box this. Okay, I'll box it in red. Okay. So this is the k-means clustering error. Okay. So very simple. Okay. Very intuitive clustering error. And, you know, the task is simple, right? Output a clustering of the data, which is a collection of k subsets that are disjoint and cover the data. That minimizes the clustering error. Okay. So we could take the output. So the output of clustering is exactly the subsets S1, S2 up to Sk and the corresponding means mu1, mu2 up to mu k. Okay. Go minimize this, you know, nice simple error metric, you know, and output for me the subsets and the centers of those clusters. So the subsets are called the clusters, and the centers of the clusters, well, they're the cluster centers. Okay. Well, unfortunately, it turns out that this problem is very, very hard to solve computationally. Okay. And in a formal sense. So it's an NP-hard problem. Oh well. Okay. And we've seen NP-hard problems before. You know, the first NP-hard problem we saw was when we were talking about the linear model and classification. Can we find the linear model that minimizes the probability, that minimizes the number of in-sample mistakes? NP-hard. Okay. So machine learning is a source of many NP-hard problems, but we still need to do it. So we're going to build a heuristic, you know, which is an example of an alternating algorithm, which comes from a family of EM kind of algorithms, which we'll see later. Okay. That is very good at solving this problem. It produces good solutions. Of course, in the worst case, it can be far from optimal because the problem is NP-hard. Okay, but we need to do something. So let's develop the alternating algorithm, and that alternating algorithm is called Lloyd's algorithm. So Lloyd's algorithm. Okay. So there's no algorithm that can guarantee finding the optimal clustering that minimizes this error in polynomial time, or at least none that we know of. Okay. So Lloyd's algorithm is an example of what's called an alternating algorithm. Okay, because it alternates between doing one thing and then another. And it actually comes from a family of algorithms. So it's a special kind of alternating algorithm, which can be posed as an EM kind of algorithm. But we won't get into those details. Let me show you the algorithm. It's very intuitive. Okay? It says that, you know, we don't know how to solve this problem in general, but, okay, if you give me centers, mu1, mu2 up to mu j. Okay. Well, then I know how to solve this problem. So if you were to tell me what are the optimal centers, then I know how to solve the problem. Okay. Then I can solve the problem greedily. Okay. What does that mean? Well, if you've told me the centers, then there's a very simple prescription for identifying the subsets. For each center is going to correspond to a subset. And what am I going to do? I'm going to take each data point and assign it to the center that's closest. Okay. So you can think of the centers, okay, in two dimensions. If you give me the centers define Voronoi regions. Okay. You know, we've seen this before. Okay. So there's that guy, then there's that guy, that guy. So each center defines, in some sense, a Voronoi region. Okay. And now you look at the data points, okay, and you assign data points to the center that owns the Voronoi region to which that data point belongs. So if these are the centers in black, then the clusters are defined exactly by the points that lie in each Voronoi region. Okay? And it's easy to see that that's optimal because, you know, by definition, the distance from this data point to this center is closer than its distance to any of the other centers. So it's going to minimize that distance from the data point to its corresponding center. Okay, so each data point can be minimized greedily, and if you can do that greedily for each data point, that's optimal. Okay, very easy. Okay, the second observation is, if you give me subsets, if you give me subsets S1, S2 up to Sk, then I can construct the optimal centers. Then the optimal centers are easy to construct. Okay, and why is that? It turns out that that's related to the fact that we're looking at the squared errors. Okay, so now you've told me which data points are in each cluster. Okay, and because we're using the squared error, it's easy to construct the centers of the clusters. If we were not using the squared error, it might be much harder. Okay, and how? Well, it's an easy exercise for you to show that the center mu j, which minimizes, or thus the ej, which is the sum over x in Sj, so the sum of the data in my cluster Sj of the norm of x minus mu j squared. So this is the sum of squared deviations. The center which minimizes this is exactly the mean. So mu j star is equal to the sum from of all x in Sj of x, okay, divided by the size of Sj. So it's just the mean data point. And what's that? That's the mean data point in Sj. Okay, so that's interesting. If you told me what are the optimal centers, or if you gave me a set of centers and said you're restricted to use those centers, I can construct the optimal subsets. If you gave me the subsets and said I'm restricted to use those subsets, I can identify the optimal centers. Okay, and those two observations exactly together lead to this alternating algorithm. So let me show you the Lloyd's algorithm. So Lloyd's algorithm is very simple. Lloyd's algorithm. Okay. Step 1. Okay. Find centers. Centers mu1, mu2, mu3 up to mu k. How? Okay. So if it's the beginning of the algorithm, randomly. So either randomly for the beginning or as the mean vector in the respective cluster Sj. Okay. So that's the first step. Okay. So you randomly choose data points xn. Okay, so each center is a randomly chosen data point, okay, at the beginning. And as the algorithm progresses, you will construct the centers to be optimal for whatever the current clustering is. Okay, and once you have centers, assign data to centers greedily using the following algorithm. Data point xj gets assigned to the center, or let's call it x little n, gets assigned to the center which minimizes the distance to xn. Okay, so argmin over j. So find me the center that minimizes the distance to xn, and that's the center to which I assign xn. So you assign your data points to centers, okay, and always making sure that I assign the data point to the center that's closest. Okay? That gives me a clustering, a partition into subsets. Okay? Now that I have a partition into subsets, I go back, repeat until convergence. Okay. I go back and reassign and compute means, okay, according to the mean vector of the corresponding clusters. Then I reassign data points to centers. Then I recompute new centers as means, reassign, and so on. Now, how do I know that this is going to converge? The reason I know that this is going to converge is that in each step of the algorithm, okay, if anything changes, it is if anything changes, it is because either this in this step or this step. If anything changes, that means that this error function strictly improved. So let's see. Okay. If you have your clustering, okay, and you have your centers, and you decide to move a data point from one center to another, it's only because that center is closer. Okay, so that'll strictly decrease the error. And in this setting, if any of the centers are not the corresponding means, then by moving the center to the corresponding mean, you strictly decrease the error. Okay, so each of these steps strictly decreases the error. Okay, so every step here strictly decreases the error. So every time the clustering changes, the error strictly decreases. Okay, and the error cannot continuously strictly decrease forever because there are only a finite number of clusterings. So eventually you have to hit the bottom. Okay, so this algorithm is guaranteed to change, is guaranteed to converge after some finite number of iterations. But the problem is there are exponentially many clusterings, so it can take a very long time to converge, and it's not necessarily the case that it converges to the optimal. So there are many local minima in this, in this error function, and this can converge to a local minimum. But in practice, it works very well. Let's have a look at some examples. Okay, so let's see some examples. Let's see Lloyd's algorithm working on some data. Okay, so on the right is some data that we've seen before. Now a slight improvement in the initial step in Lloyd's algorithm, which picks centers randomly, is to pick centers that are well separated. So start with a random data point, pick as the first center, pick the next center as far away as possible, and then the next one as far away from those two, and so on. That gives us, these black centers. Okay, and the next step is to assign to each center the data points, the data that's closest to that center. That constructs, in this example, 5 clusters. Okay, and now you update the centers of those clusters, okay, to the mean data point within each cluster, and you can see this update, and you can keep doing this update over and over again, but it converges very quickly. It very quickly converges. Okay. Now, let me show you an application of this k-means clustering algorithm to the radial basis function network. Remember, the first step was to find centers, so we use Lloyd's algorithm to find centers. And look, okay, if we do 10 center radial basis function network, why 10? Well, I picked that because I know something about the digits data. There are 10 classes. And look at the beautiful, separator that we get. Okay. Now, if I pick a 300 center RBF network, then we clearly have overfitting. And so, if you're going to pick 300 centers, be ready to regularize. So, for example, you can use regression for classification and then regularize the regression to get your final classifier, or or you should use something like cross-validation to pick the number of centers. Let's talk about probability density estimation. Okay, so now remember, the probability distribution was instrumental in allowing us to accomplish the first step of machine learning. And how? Because it required that we generate the training data using the probability distribution, and the test data must come from the same probability distribution. And that's when we got the first step, that E in is approximately E out. Well, now we're talking about how to estimate the probability density. So why is this a similarity-based technique? Well, it's because the probability P of X measures how likely it is to generate inputs similar to X. Okay, and so similarity-based techniques are going to be relevant. Now, probability density estimation is unsupervised. You only have the X values. So it naturally fits within our peak at unsupervised learning. And it also has a natural relationship to clustering. Because think of the probability density as a much finer, much softer representation of a clustering. Why? Because you can think of the clusters as regions of high probability. When you generate data, they'll cluster into those regions of high probability. So if I show you the probability density, you might be able to extract clusters, by just looking at, let's say local maxima of the probability density. Okay. Now, we won't spend too much time on the non-parametric approaches to probability density estimation, just like the non-parametric RBF. Okay, we'll look at that quickly, but make the immediate jump to the analogous, parametric approaches to density estimation. Just like there's the RBF network, the analog to the RBF network is the Gaussian Mixture Model. So we'll move to that, and that's a very powerful technique for probability density estimation. So let's start with the non-parametric version of the RBF for density estimation, and it's typically called the Poisson-Windows estimate. The idea is very simple. Okay? So here I'm showing you, 1, 2, 3, 4, 5, 6 data points. What do? You just place a bump of volume 1 over n. 1 over n because each data point accounts for, in some sense, 1 over n of the probability. So you place a bump of this fixed volume on each data point. That corresponds to the probability density contribution from, the first data point is a bump here, then the second data point is a bump here, then the third, a bump, a bump, a bump, a bump. Okay. So now you have, in this example, 6 bumps, and then you just add up those bumps. Okay. Now, if each individual bump is normalized to 1 over n, when you add up those bumps, the total integral will be 1. And so it's a correctly normalized probability density. Okay. And you see here what the Poisson window estimate gives us for these 6 data points. And if you look at the probability density, you can see sort of 3 local maxima, which are the regions of high probability. So it suggests that this data will cluster into 3 clusters. So that's the relationship between the probability density and clustering. Okay. Now, if we want the mathematical prescription for this blue curve, this probability density, so our estimate p hat of x, okay, is 1 over n. That corresponds to the bumps of size 1 over n. Your Gaussian kernel, which is the bump, okay, so now we're computing the density at x. So it's the Gaussian kernel evaluated at x minus the data point xi. Now there's a scale parameter, and to get the normalization right, if you compute distances with respect to your scale parameter, you have to renormalize by 1 over the scale parameter to the power d. Okay, and so you can sit down and work this math. Let me show you the results of the non-parametric RBF density estimator and the digits data, and it's quite intuitive. So on the left is the two-dimensional version where I'm now looking at the intensity is x and the symmetry is y. Okay, and we see the regions of high probability are these bumps where the 1s occur, the 0s, and so on and so forth. So you get this nice mountainous region. And if I go back, you might ask, what should be the width of the bumps? Well, that's governed by this scale parameter r. Okay, and you can set it in almost the same way as we did for the non-parametric RBF estimator. You set r so that it's approximately giving you convergence like 1 over root n. Okay, or 1 over the dth root of n. Okay, so here's the probability density estimate. On the right, I'm showing you the typical view that we use when we look at probability densities, because it's a little bit tough to figure out what's going on from the picture on the left. But on the right, we show the same x and y, so intensity and symmetry. But now what we plot are contours of constant probability, or contours of constant probability density. So red is high probability density and blue is low. Okay, and now it's immediately clear sort of where are the clusters. So I can see 1 cluster here, maybe 2 clusters here, 3, 4, 5, 6, 7, 8, and maybe a few, sparse clusters outside. Okay, so corresponding to the clustering that we showed you for the k-means clustering of the digits data, here's the equivalent picture for the density estimate, the non-parametric RBF density estimate. And it's quite beautiful. Okay, now, let's immediately jump to the analog for the density estimation setting of the RBF network. Okay, so the idea is, the basic idea is we're not going to place, a bump on each data point. We're going to pick a bunch of centers, take k of them, and on which we'll place bumps. Okay, and now we'll give us the flexibility to place the bumps anywhere, not just at data points, and we might not necessarily require the bumps to be spherically symmetric, so the bumps will have a position and a shape. Okay, and let's go to the board and discuss the Gaussian Mixture Model. It's a very powerful, very commonly used model. We are going to talk about the Gaussian Mixture Model. Okay, so the Gaussian Mixture Model. Now, I showed you the Poisson windows, which puts a bump on every data point. That's kind of like the non-parametric RBF. So Poisson windows. Okay, so there's a bump on each data point. That's analogous to the non-parametric RBF. Okay, and so the Gaussian mixture model basically is analogous to the parametric RBF network. So parametric RBF network. And so instead of putting a bump on each data point, you fix a number k, the number of bumps, and you put the bumps at k bump centers. Okay, so a bump on each of k bump centers. Okay, and that's the Gaussian mixture model, which we typically abbreviate to GMM. Okay, so this is the GMM, the Gaussian mixture model. Okay, now let me illustrate with a bunch of data points. So imagine you have a bunch of data points. Okay, and you might decide that you're going to model this with 4 clusters or 4 centers. So you might place 4 centers, okay, at different points. Okay, those are my 4 centers. So you have k centers in general. So the center positions will be vectors mu1, mu2, mu3 up to mu_k. So think of these as the bump centers. Okay, and now these bumps each have a shape. Okay, now spherical bumps would be spherical or circles in 2 dimensions, but we are going to allow the bumps to have a more general shape. Okay, so for example, this bump might have this shape. So okay, and this bump might have that shape, and this bump might have that shape, and this bump might have this shape. Okay, so you can think of the shape as being specified by sort of a rotation, an angle. Okay, and then a major and a minor axis. Okay, and so those are that shape is specified by what we call the covariance matrix of the bump. Okay, so you'll have shape parameters sigma 1, sigma 2, sigma 3, sigma k. Okay, these are the bump shapes. Okay. And you could also imagine that we get to specify the bump weights. So how much of the data sits under each bump. So we might think of bump weights, W1, W2, W3, and so on up to WK. These are bump weights. Or how much data, proportionately speaking, relatively speaking, how much data sits under each bump. Okay, when I say sits, of course, that's metaphorically. Okay, and so that's the basic idea. So we get to pick, so we're going to model this data, we're going to try to extract the density, the probability density models the data. In other words, you could think of it as having generated the data. Okay, so we're going to model this data by picking k bump centers, okay, k shapes, okay, and the weights of each bump. Okay, and once we have picked these, we have the density. Okay, and so the probability density p hat of x. So our estimate p hat of x, p hat of x. Let's call it p hat because it's not p. P is the true. Okay, p hat of x is going to equal the sum over all our bumps. So this is now you place the bump at over each center, and if you're at some other random point x, okay, you take the contribution from each bump and add. So it's the sum from little k equals 1 to big K of the weight of the bump k, WK, and the formula for the bump, the probability density that corresponds to the bump. So we'll call that n of x. Okay, and this distribution, okay, this density for a bump n of x, okay, will typically depend on the bump centers. Okay, it'll depend on mu k, and it'll depend on sigma k. its shape. So it will depend on its center and its shape, sigma k. Okay? And so this is the form. This is a general, you can think of this as a general formula that, you know, computes a probability density as what's called a mixture, a weighted mixture of bump densities. Okay, where in our case, the bump densities depend on the center of the bump and the shape of the bump. Okay, and so let me tell you the kind of bump that corresponds to the Gaussian mixture model. It's basically that this bump is a Gaussian density. So n of x, the Gaussian density, given the center, mu k, and the let me call it just mu now. So given the center parameter and the shape parameter. So now when we're talking about the Gaussian, this is typically called the mean. Okay, and this is typically called the covariance matrix, and indeed for a very good reason, because if you generated data from this Gaussian, the expected data point, the average value, the average, which is a vector valued average, the average data point will indeed be the mean, and the covariance matrix of the data will indeed be this parameter sigma, the covariance matrix. Okay, so the Gaussian distribution is given by 1 over 2 pi to the d over 2. Okay, so you're in some, I'm giving you the general version, which is in some arbitrary dimension d. The determinant of sigma, so this is the notation for the determinant of sigma to the 1/2. Okay, then we have the exponential, the Gaussian e to the minus 1/2 x minus mu transpose sigma inverse x minus mu. Okay, so this is the Gaussian density. And I'll tell you some facts about the Gaussian density. If you generated a lot of data using the Gaussian density, you know, and then looked at the average data point. So if you generated data x1, x2, x3, and so on up to x, you know, let's call it m. Okay, then the average or the sum, so the expected data point, so the sum of xi 1 over m, this converges to the expected data point, so the expected value of x. Okay, which is mu. So this center is not only the center of where we place the bump, but it also happens to be the average data point if you were to generate. Okay, and it also turns out that if you compute the average of the outer products, so 1 over m, the sum of xi transpose. So this is a d-dimensional vector. This is d by 1. This is 1 by d. So this is a d by d matrix, and you're taking the average of d by d matrices. This converges to the expected value of xx transpose, which is mu transpose plus sigma. Okay, so these are just facts. So you can go and, you know, perform the integrations that correspond to these expectations and derive this, or look in a textbook, you know, your pick. Okay, but these are facts about the Gaussian distribution. So it's very nice that the center parameter corresponds to the average data point, and the shape parameter corresponds to the covariance matrix of the data. If you take this guy and subtract mu transpose, you get exactly the covariance matrix. Okay, so now in order to interpret this as a weighted, you know, sum of bumps, you know, we typically want that the wk are greater equal to 0, and the sum of the wk is equal to 1. So it's a k equals 1 to big K. So this is a weighted sum of bump densities. You can think of this as a weighted sum of bump densities. Okay, so this is the basic idea. The basic idea is that you know, we have a mixture density that we're trying to fit to the data. It corresponds to placing the centers at, you know, clusters of the data, and choosing the shapes of each bump, and also choosing the weight of each bump. How much data is inside that bump? Okay, and what do we get to do? We get to pick all these parameters. So we will pick all these parameters so that we sort of match the data. So we get to pick. Okay, so we get to pick the centers. Okay, shapes and the weights. So we get to pick the weights, Wj, the centers, μj, and the shapes, sigma j, for j equals 1 to big K. Okay, so we get to. So how should we pick them? Well, we should somehow pick these parameters that we get to pick in order to fit the data. Okay, so we saw this before. A very common approach is to use the method of maximum likelihood. So since this is a density, it is explicitly quantifying the chances, the probability to generate a data point X. And we've generated a bunch of data, so we could try to maximize the probability of generating the data. So pick the parameters to maximize the probability to generate the data, which is your x1, x2 up to xn. So to maximize the probability to generate your data, this is the method of maximum likelihood. Okay, and indeed, the method of maximum likelihood. Okay, and indeed you can set up the likelihood and go ahead and try to maximize that iteratively using gradient descent. There are many local minima and so on and so forth, but you can do that. Okay. Now what I'm going to describe for you is a very nice, elegant algorithm. It results from an expectation maximization approach, and it is another example of an alternating algorithm. We already saw one for k-means. So we'll continue that theme, and I'll show you another alternating algorithm. It is an expectation maximization algorithm. Okay. And you can see all the details and sort of the rigorous derivation of this algorithm in the E appendix, okay, associated with this E chapter. Okay, on the expectation maximization algorithm. So in general, expectation maximization is a very powerful tool for maximizing likelihood. Okay, it doesn't go to the global maximum, but it's an iterative algorithm that's easy to implement. It usually results in a very intuitive algorithm. Okay, and that's what I'm going to show you. Okay. And the basic idea is, we're going to introduce what's called a hidden variable. Okay, and this or sometimes called a latent variable. And if you knew this latent variable, then it's easy to set all the parameters without any effort. Okay, and so what we do, just like with if we knew the centers of the K clustering, it's easy to figure out what's the optimal clustering. Okay, or if we knew the clusters, then it's easy to figure out the centers. Okay, so it's similar in this situation. If we knew which data points belong to each bump, okay, then we can compute the mean of the bump and the covariance matrix for the bump. Okay, and in some sense, the weight of the bump is just the fraction of data that belong to that bump. So if we knew that, we could easily compute all our parameters. Okay, and so what we're going to do is a similar algorithm which says, supposing we know that. Okay, supposing we know that, then we can compute all the parameters, and then we'll use the parameters to estimate how much data is inside each bump, and then repeat. So that's the basic idea. Okay. So the basic idea is, if we know which data belong to bump, let's say J, then that easily will tell us what are Wj, μj, and sigma j. And then if we know Wj, μj, sigma j, okay, if we know all of those, then we can figure out which data belongs to bump j. Which data belongs to bump j. Okay? And so what we do is similar to the k-means algorithm. We alternate. We pretend like we know which data belongs to which bumps, and then optimize the bump parameters. Then we use the bump parameters to figure out, which data belongs to each bump. So just like in k-means, we pretend we know the clusters, we can get the centers. We know the centers, we can get the new clusters, and so on. Repeat. Okay, so that's the basic idea. Okay. Now, so let's describe the first step. The first step is we have to initialize, and one way to initialize is just using a K clustering. That gets us, initial data that belongs to each bump. Okay, so you could do K clustering. Okay, so random assignment of data to each bump. Okay, but initialize. So let me say initialize. Okay. So for example, using a K clustering. So that tells you what data belongs to each bump. Okay. So in general, okay, let us define gamma n j. Okay. So n is the data point xn, and j is the bump j. Okay. So I'm going to define gamma nj is equal to the part of data point xn, the part, okay, I'll put that in quotes, i.e. fraction of data point xn that belongs to bump j. Okay, so you might be thinking, what? Why do I need a part of the data point to belong to bump j? Doesn't the data point either belong or not? And that's true in a hard clustering. Okay, but the interesting thing about the density estimation and the Gaussian mixture model is, let's take, for example, this data point here. So let's take this data point here. We don't have to commit to the data point belonging exclusively to this bump. We can say, for example, that this data point half belongs to this bump and half to that bump, and basically 0 to this, 0 to that. Okay, so we're allowing fractional bump memberships. Now, of course, when we do the initialization using clustering, that's going to assign each data point, exclusively to one bump or the other. So it's possible that gamma nj. Okay, so think of gamma as a matrix, sometimes called the clustering matrix. Okay, so gamma has the data points along this dimension, so this is n, and the clusters along this dimension, so this is k. This is n. Okay, so this is xn, for example. A row corresponds to xn. Okay, and if it's all 0 everywhere except for one spot, which is 1, okay, then we see that data point belongs to exclusively to one cluster. But we're allowing these to be fractional. So what we require is that the sum in a row is 1, and they're all positive. So gamma nj is non-negative, and the sum over j of gamma nj is equal to 1. So a data point can belong to a part of a data point can belong to a cluster, okay, a bump, but at the end of the day, the entire data point must be allocated. Okay? So this is a generalization of the clustering problem, where in the clustering problem, we require that each data point belong exclusively to one and only one cluster. Okay? But now we're doing density estimation, so we can allow the chances that this data point was generated by that cluster to be some value, and the chances that this data point was generated by that cluster to be some other value. Okay, and so those chances kind of relate to what fraction of this data point belongs to this bump and what fraction belongs to that bump. Okay, all right. So now, okay, I'll keep this part here, but we don't need the explicit formula anymore. Well, although we do have it. Okay, so let's keep the formula. Okay. And now, let me show you the algorithm in action. So this bump membership matrix gamma is very crucial to the algorithm. Okay? And we have started by initializing using a K clustering. So that means we have initialized the bump memberships. So assume, step 1, assume you know the bump memberships gamma and j. So you know the bump memberships gamma and j. Then, okay, let's figure out, how much data belongs to each bump. Okay, so let's call that n sub j. How much data belongs to bump j? Well, that's just the sum over your data points of how much of that data point belongs to bump j. That's just gamma n j. So this is how much of data point n belongs to bump j, and we've added that across all data points. So you can think of it as the column in this matrix. Okay? So this column is bump j, Okay, and how much of each data point belongs to bump j? I'm going to add that all up. Right? That tells me how many data points, okay, in terms of adding up the fractions of data points, how many data points belong to bump j. The total number of data points, n, is just equal to the sum over j of nj. And that comes, if you sum this over j, you'll find that it equals, n, okay, because of this condition, that the sum of the rows are 1. So if you sum over j of nj, basically you're summing every entry in this matrix, okay, which is the sum of n rows, and each row sums to 1, so you get n. Okay, that's good. Okay. Now, the volume, the amount of data that belongs to bump j is the weight of bump j. So wj is just equal to nj divided by n. Very easy update. Okay. And let's see, what about the center? Well, we said that, assuming that all the data that belongs to the bump, was generated by the Gaussian for that bump, well, then the average data point that belongs to that bump is exactly the center. So mu j is equal to the sum, okay, over all data that belongs to that bump of the data point xn times the fraction of it that belongs to the bump. So the sum from n equals 1 to big N. So this is the fraction of data point n that belongs to bump j. Okay. So I'm adding up the data points that belong to bump j, weighted by their fraction. Okay, but now I need to take the average. So I divide by the number of data points that belong to bump j. Okay. And I can get the shape parameter, sigma j, okay, is the average of the outer products. So it's equal to, sigma sub j is the average of the outer product. So it's 1 over n sub j, the sum over all data points, okay, the fraction of the data point that belongs to the bump, okay, times the outer product xn transpose. Okay. So sigma sub j, sigma is the average outer product minus the mean outer product. So minus mu j transpose. Okay. And there I have updated all the parameters. Updated all the parameters. Okay. So if I know the bump memberships, which I start off by knowing, then I can get updates for all the parameters. But now I can update the bump memberships. So step 2, update the bump memberships. Okay. So gamma nj is going to equal, okay, so now you can think of the probability density. So the probability is the probability that xn came from bump j divided by, the total probability density. So this is the probability density that xn came from bump j divided by the sum of all the probability densities for each bump. So in other words, normalized, so that it must have come from some bump, divided by the sum over j of the probability that xn came from bump j, which is just equal to, okay, what are the chances that the data point xn came from bump j? Well, it's the weight of that bump, so wj, times the probability density, the probability to generate that data point, assuming that it came from that bump with that center and that shape, okay, which is the normal distribution function for xn, okay, given mu j sigma j, okay, divided by the sum over all j, wj, the normal distribution for xn for mu j and sigma j. Okay. So this is the probability that a data point is generated from bump j. It's the number of data points, fractionally speaking, that reside under bump j. Okay, so it's this number, and now a data point has some probability to be generated by that bump. That's what this normal density quantifies. So the probability to pick that bump for generating the data point, and then the probability to generate that data point given that bump's center and shape. Okay, divided by that same quantity over all bumps, so that this thing now sums to 1. over the bumps. Okay. So now let me erase the actual. So this guy here, this normal density is what we had here. Okay, let me erase it. You can always look back in your notes or look it up. Okay. So that it's now clear what the 2 steps of the algorithm are. Given that you have bump memberships, update the bump parameters. Given that you have bump parameters, update the bump memberships, and rinse and repeat. Recycle. Repeat. Until convergence. And it typically converges very fast. Okay. So this is, now you can see the formal derivation of this as an expectation maximization algorithm. Okay. And one can show that this algorithm is guaranteed to improve the likelihood, okay, at every step. So the likelihood is always increasing, okay, but it doesn't necessarily go to the global maximum. Okay, so this is an EM. This is the EM algorithm for learning a Gaussian mixture model, and that's a beautiful model for density estimation. And this is the picture that corresponds to that model. Okay. So now let's go to the slides, and I'll show you this model in action. Okay, so what we're showing here is the 10-center Gaussian mixture model used to model the digits data. And you can see how beautifully, the 10 centers capture the various positions of all the, different types of, digits. Okay, and on the right are the density contours. So that contour plot where we have the intensity and the symmetry. Okay, and red means high probability and blue means very low probability. And in black, we have sort of identified the centers of the bumps, the centers of the Gaussians, and you can see how they're spread out, to capture the various digits. And it's very instructive to compare the Gaussian mixture model on the right with 10 centers and the 10 clustering. So the k-means algorithm with 10 centers. So the k-means algorithm gives a lot of information, but look at how beautifully the Gaussian mixture model, shows you, highlights the clusters and shows you the extent of each cluster. I mean, it's very similar to the k-means clustering, but the Gaussian mixture model is a soft version of clustering. Okay, it's a very powerful tool for modeling and organizing data, the Gaussian mixture model. So is clustering, by the way. So, okay, that concludes our peek at unsupervised learning. Basically, how do you organize the data? How do you model the data? So on the one hand, k-clustering organizes the data into k clusters. The Gaussian mixture model organizes the data into k mixtures of a density, which in this case is a Gaussian, and then you can extract clusters from the density if you want. It's a soft version of clustering. Okay, so that's unsupervised learning. It's a huge field. We've just touched on it, and with that, we're checking out. See you next time.